Hey guys, so this is the makeup of the discussion that we missed this last week because of Thanksgiving. So what I've done is I've posted the discussion 14. It has some statics problems and a few extra fluid problems to get you guys prepared for the test. So we're going to go over those via video. Now if you feel comfortable with the answers that are already posted online, you don't need to watch this. But this is for those that didn't understand the discussion notes. So let's start off with statics problem number 1. I'll break it up into the statics videos and the hydrostatics videos. That way you don't have to watch all of them. So problem number 1, let me just explain one thing. So sometimes I tell you guys why I do the problems I do. The statics really isn't that hard. It's sum of forces is equal to 0 and sum of moments is equal to 0. You guys know how to do this. You guys were doing more complicated problems where you guys had acceleration. So what I think is new for you guys is seeing the different kind of reaction forces. So for instance, when we have a beam sticking out, you can also think of this as a cantilever. So a cantilever would be something like this, where a load could be applied on it at the end. And this would have a reactionary force in the x, y, and a reactionary moment. Whereas something like a pin joint, if I remove this, and if I put a pin and a roller, I'm not even sure you guys can see this actually, these have different kinds of reaction forces in them. So what this worksheet for the statics was trying to get you guys used to was seeing the reaction forces for different kinds of members. And in fact, none of these actually look at internal forces, and you guys did that for the latter problem. You guys would have had to break it up and look at internal forces. So these are quite simple problems compared to what you guys have actually done. But I wanted to give you guys a little bit of extra practice on what reactions you might see. Okay, so let's start off. So this is the problem for number 1. And as I've already stated, what you're looking at is right here you're going to have 3 reactions. You're actually going to have a reactionary force in the y, a reactionary force in the x, and a reactionary moment. And that's going to actually, basically it puts the forces into the ground. It's how the forces that are exerted on this get transferred. So the forces that are exerted are these 20 kilonewtons. Your GSI was a little lazy, so she didn't put them on all of these. And then what ends up happening is that there's a cable. So the cable goes around a pulley and gets connected to the ground. So we have another force there. And so this is the point at which in the class I'd ask you guys what's the first step. And everybody in a big uniforming boom would say a free body diagram. That's what we would hope for. So that's what I've done here. So we have our 20 kilonewton forces that are hanging off. Those are external forces. So again, none of the problems I've given you guys look at the internal forces. I suppose because we've cut it here, you can consider that an internal force, but it really isn't. So again, the cable, we don't take that apart. It's all a part of itself. We don't look at the pulley. We keep it all connected, and we know that there's a 150 kilonewton tension on this cable. And that's going to get connected to the ground. And then finally we have our 3 reaction forces. And again, because this is something like a cantilever beam, just sticking out of the ground, we have all 3. Okay? So if you see a beam sticking out of the ground, this is the kind of analysis you're going to want to do. So we do our sum of forces equation. So we have sum of forces in the x. Again, I want you guys to write it down, sum of forces in the x. I want you to tell which way is positive. So which way you assume to be positive. Again, you can assume the other way is going to be positive. But you need to tell the size. Sum of forces is equal to 0, otherwise this thing accelerates. So this is in the past where you guys were putting m times ax, but now the acceleration is equal to 0 because this thing is static. So we don't want it to move. And then we list our forces. And again, the forces are going to go in the way that you've assumed them to be. You can assume it wrong, and that's fine because the answer is going to come out negative, which is exactly what I get in this problem here. So I say, well, EX plus 4.5 divided by 7.5 times 150. So again, we're going to take the X component of this 150. And if we look at what that is, then it's 4.5 in the X. And if you add the dimensions I've given you in the Y, they come out to 6. It was a little obnoxious I did it that way. And if you take 4.5 squared plus 6 squared, square root that, you get that the hypotenuse is 7.5. Okay? So this dimension would be 7.5. So if we break this up into its components, what we would do is we take 4.5 over 7.5 times 150, and that gives us the only force that this is going to try to counterbalance is the x component of this. These are all in the vertical, this is in the vertical, so the only thing it's trying to counterbalance is this guy. And that's exactly what we get. So Ex is negative 90 kilonewtons. And it's a good check to think about, does this make sense? And it does, because if this has, so if we look at the components it has a downward component and an over to the, well, if I'm looking this way, it would have to the left, right, to the left force. And it doesn't make sense that this would also be acting to the left, as I've assumed it. So it should be acting the other way. It should act to the right. Okay. So now let's look at the sum of forces in the y. We've assumed positive is going up. We've assumed that the acceleration is going to be 0. We hope so. Oh, sorry, it should be Ey. This is our reaction force. Minus the 4 times 20, so I've taken into account all 4 of those right here. Minus 6 over 7.5 times 150. And we get Ey is 200. And that makes sense that it's going to be positive because we've assumed it's going up. Everything else is coming down. Okay, so now the moment. Moments could be 0, okay? And not everything is going to have a reactionary moment, but a cantilever does. Tell the QSI which way you want to assume is positive, clockwise, counterclockwise. This time I've assumed counterclockwise. Now notice, so what I'm going to do is I've done each of these separately because they cause a different moment at this point. So again, tell the QSI where you're taking that moment. I'm taking about point E. And if you look at the solutions I've posted, I wrote around point O. That doesn't make sense. There is no point O. So make a change right now. Point E. Okay? Right there. And so each of these has a different moment arm to that point E. And that's why we have to do them separately. Okay? You also want to be careful here when you do the moments. You can assume the force is going to go either way. And similarly with the moment. For instance, the reactionary moment, I've assumed it to be positive. But if you assume a force, for instance, when you did the ladder problem, you need everything to match up. And so when you guys are doing your problem, and if you're finding out that the answers doesn't make sense, that's probably the most likely thing is that one of the forces, if you've assumed it in some case to be positive here, you probably didn't understand or didn't get the right sign notation for the way you've assumed it. So whatever you assume, stick with that convention. The other most common problem is negative signs, and just plain algebra. Unfortunately, these have hairy algebra, tedious. So let's continue. So 20 times 7.2, that takes care of this guy. We go on, 20 times 5.4, 20 times 3.6, 20 times 1.8. And notice they're all on this side of the point E. So they're all going to cause a positive moment the way we've assumed it. They're all going to cause a counterclockwise moment. Now this guy, he's obviously going to cause a clockwise moment. And notice that it's only going to be the horizontal component that's going to cause this. Because remember, the vertical component passes through that point that we're looking at, that we're interested in. And remember, if the force passes through that point, he's not going to cause a moment. So, we do not care about the vertical component of that 150 because it's not going to cause a moment. So what we're going to do is we're going to care about this horizontal. So that's exactly what we do here. Let's see. And something seems off. So let me double check my work. Let's see. One second.